Hello, my friends. Hello, my high frequency microwave millimeter wave circuit designers. Welcome back. I am Dr. Mohamed Nezami, and this is the six-part video in my series on the design of slotted waveguide antenna array design in 3D model. Now, my friends and colleagues, this is my YouTube channel. I would appreciate if you would be kind to visit. And I have been doing this series on slotted waveguide antenna array design and 3D modeling. These are antennas that are very important in radar and SATCOM, and recently also they're starting to pick up some applications in the motor vehicle safety radars and some other applications as well. I started the series. This is six-part. You can go back and review and view these parts. I started from a single um, element to basically where I stopped, and you can please refer back to the channel. I would appreciate if you can go back to my channel here. I would appreciate if you subscribe, please. That keeps the channel alive, and please share it if you could. I would appreciate it. My playlist on the slotted antenna waveguides right here. You can go back and refer to this and see all these. I've got other things in there as well. You can view various techniques and devices in the high frequency. Okay, so today, in today's part, what I'm going to do is I'm going to continue basically where I started. First of all, I would like to flash this by you. This is my contact email. I'm a freelance RF and microwave circuit designer. I take your concept or your defined requirements, work with you on specifications and drafting a concept to architecting the system modeling using system view and ADS and other packages as well, ANSYS as well. And then I come in and design actually active passive both PC boards for you and turn in the complete PCB, PCBA with bill of material to you remotely, completely, and at a very reasonable rate. You can contact me. My first consultation, few hours, is free always. Don't hesitate to call in and schedule Zoom or Teams review meeting where we could look at what you have and could work together. I have several clients that are very happy, and several products this year that has spun off in Europe, US, and in the Middle East as well, and even in India. Okay, slotted waveguide antennas, you can refer back to my parts, part 1 through part 5, but basically one of the examples that you can see here is a weather radar in I think this was taken out of a Cessna airplane, small airplane, but you can see these as well in large jumbo jets in the nose, and there are hundreds of elements, okay? But this is what I wanted to do, and they come in varieties, so they could be rounded, they could be staggered like these. The design, please review, go back to my first part and second and third part, and you will see the design principles, but they're very simple. Basically, we've got a waveguide, okay, that has some slots that are distributed above and below the center line of the broad wall. And there are certain number of equations that you can use basically to define the width, the length of these, and the distance from the feed point and the distance from the short end. and the distance between the slots. So these are very simple. We went through them. I have a MATLAB code in one of the previous videos that you can calculate this. Now, whether you're feeding on the side or whether you're feeding in the middle somewhere, you could utilize this inclined slotted waveguide feeder. And likewise, it has the same thing, except everything in here is a half wavelength spaced from the short and between the elements. These are here, of course, at the end it's short, so we need a quarter wavelength. And previously, I went through the model of this as a transmission line where these slots are basically parallel loads. That's why you see at a quarter wavelength, you need an open. At the end, you need an electrical open, which is physically short, but it's really a quarter wavelength from the center of the slot. Where the other ones in here are basically these feeder ones for the stacked waveguides. They're basically in series, and that's why you see an actual physical lambda over 2. Now, I started this series with designing on HFSS basically a single waveguide with 16 slots, and we were able to get the gain of 19 plus some fractions of a dB. And of course, now this is uniformly distributed above and below the center line of the broad wall, these slots, so that we end up, this is like a linear array of 16 dipoles, a half-wave dipoles, so they're really spaced, uniformly spaced and excited uniformly, so you end up with the according to the DFT or FFT or windowing technique where it's non-windowed, so you end up with 13 dB first level of the side lobe, okay? And that's what we get here. So what usually we would do is we take this and then we end up with constructing a complete aperture like it is shown in here. Now, the equations to define the, now, of course, if you want to reduce the side lobes in here, in part 4 of my series, what I did is I went in and windowed these distances from the center line, which basically what it does, it weights the excitation level on each one of these dipoles, and that gives you, that reduces the side lobe. And I've showed you how to use MATLAB and the built-in MATLAB windowing functions, Chebyshev and Taylor, to come up with these coefficients. And then in conjunction with the design equations for the distance from the center line of the broad wall, which is defined here from Elliott in 1980s. And of course, we ended up with a much nicer radiation pattern where the side lobes are really down, okay? And you could vary this relative side lobe level, which is in here. In this case, I computed it for 40 dB below, but you can, and when you do that, you have a trade-off, a small trade-off. You lose about fractions of a dB of gain, and then the beam will broaden a little bit. Okay, but you can feel if that's too much, you can always reduce this requirements and end up with a little lower price to pay for tapering down the side lobes. Okay, so what I'm going to do is let's take this guy here. Okay, I'm going to do is actually take this and duplicate it 16 times to build basically what this is a 16 by 16. The 16 this way and 16 this way, 256 element aperture. Okay, and that's what you see here. Okay, so I did that on the on here. That's basically what we have here. So each one of these, I started out with one here and then duplicated this 16 times until I got to here. And of course, I have the feed waveguide, which is this guy here that you see here. Okay. And you can see the inclined slots, okay, that are basically in a common wall. So you can see these are the slots. Right now, I've got about 22 degree of inclination. And I showed you in one of the parts how you can optimize this by sweeping the angle and seeing where it is at. So, but basically what I end up with is that what you need to do is you need to overlap both the feed. This is the feed waveguide, and this is the radiating waveguide. This is the first one, okay? So you comment them with the same thickness so that you can hollow out the feed slots in here. And of course, the radiating slots are on the other side of this. So, and that's what you see here, of course. And of course, this is I'm feeding right here. You can see the excitation. I'm feeding right at this point here. Okay, that's the feed point. Oh, no, I'm sorry. I'm looking at okay. So this is basically we're feeding in here on this end. Okay, and right now why the feed this is basically you see that the feed waveguide is extended a half wavelength above and below the top and bottom waveguides. Okay, and when I do this, this works out really nice. So what we end up with is I end up with about 30.6 dB of gain. Now, according to theory, this matches really well because I got 19 dB out of a single element of these. And of course, when you repeat that 16 times, that's really, you can check that 19 dBi plus 10 log of 16, that gives you exactly 31.041. Okay, and that's, very much the same. You can tweak it a little bit to get closer to this number. That's in theory what you should get. The side lobes again. Now these waveguides, the slot above and below the center line of the broad wall is uniformly displaced, which means this is a rectangular windowed coefficient excitation, which means still you're going to still get 13 dB if side lobe level. And so that's what, okay, here is the beam. It looks very nice beam, pencil beam. Okay. Now the return loss is pretty good, but you can see how narrow this band this is. And that's one of the disadvantages of this waveguide. That's why the usage of this has been classically always for radars and some other, few hundred megahertz, my center frequency, of course, this was designed for 10.3 gigahertz. Okay, the EM, and you can see it in here that basically what it is, you can see the field, how it's distributed inside the waveguide vacuum, both the feed and the radiation. Okay, this is a look from the back, so you can see the excitation in here. Now, what I could do is I could reduce the side lobes, and that's going to complicate the design a little bit because now this is not, and we can't duplicate the single waveguide. The same thing here, duplicated 16 times because now we're talking the weights are different. So what you end up with a two-dimensional array of weights for the planar slots. And the way I generated this was generated for Chebyshev function in MATLAB. So you specify this and you just basically multiply the two linear ones. And in this case, it's of course square aperture, so it makes it easier. If it's not square, then that even complicates much more. But with a square one, you can see that I've got 16 here, 16 here. And what happens is that the two middle ones, they're exactly the same. And then it tapers off to the sides with a mirror image. So what you end up with really is from here to here, these ones here, these ones from here to here, they're the same mirror image of this. So you can utilize, that fact to reduce the complexity of this. Same thing for Taylor. You can Taylor weights if you like to generate them using Taylor polynomial. Okay, so let's go back to here. And so this is the design. First, I want to show the, okay, so the gain, like I said, you can see that it's here it is, it's 30.6 dB of gain in this case. The side lobes are nice, and of course the 3D polar beam is pretty nice. Again, it's computed here is 30.6 dBi. And let's see, let's look at the E field of this. So we're gonna, oh, okay. Okay, so this is an overlap of the E field in the surrounding air. I want to remove that, so let's take that and just leave this here. Okay, here it is. So you can see that the E field is fed right here, and it propagates down the feed waveguide, and it radiates out through the slot into the branches, the radiating branches. And of course, the radiating branches, the E field, the signal propagates on both left and hand. So let's animate this so you can see a little bit of a movie on this. Okay, it's taking a few moments. Okay, still going. Now, of course, the other thing that I want to talk about is the okay, so let's see. Now it's running now. So you can see now, let's track it from here. So the E field, the feeding point is right here. We feed, and then the E field propagates through the feed waveguide. Okay, and then as you can see how it couples out into the radiating waveguide, each one, and you can see how the okay, I'll let you watch this so you can see how neat this is. Of course, this is nice, and it has been very effective tool while I was doing this, while I was constructing this. Sometimes you make errors in the construction of this, and one way to discover your errors other than just going in here and using the model function, using measurements. Okay, you could actually cite it, and then you'll see immediately where where the E field is abnormal, not normal. Like you can see in here, when you look at this like this, you should see a complete symmetry, and you could see consistency. If you see anything that is, if you made any errors in any of the branch waveguides, you will automatically spot it. Okay. Now, the other thing that I forgot to tell you, now I did design this using the standard waveguide with, let me see here, the dimensions, the expand waveguide with a 22.86 millimeter, and the B width is height is 10.16 millimeters. But that's really the branches. That's these guys here. Okay. Now let me stop this. That's these guys. But if you do this, you really now what happens is that because you need to space these slots, you need to space them at a half wavelength. Okay. You need to the distance between these is always, as you can see here. Let's see. Let's do measurements position. If you look at the distance between any of the center of these And of course, this is along the x-axis. You can see the x-axis, it's 18.89. And that's basically a half wavelength, okay? And then the end in here, of course, between the center and the edge of the waveguide, that's half of that, which is what you can see there is 9.4, because this is quarter wavelength. Now, if you try to do that, then of course these here also, the distance between these waveguides and here is a half wavelength as well. When I say half wavelength, that doesn't mean it's a free space half wavelength. That's waveguide half wavelength. This one is different. This waveguide in here cannot be the same as these waveguides because you cannot really force. Otherwise, you would have an overlap in the middle. You can't physically make the feed waveguide the same as this one here, unfortunately. So that's what happens, and that's why this one is a little different. In fact, this one, the width and height of that one, let me just see that. Okay, here it is. The B height is 9 millimeter, and then the the broad wall is 18, where this one was 22.86. And you can see that, of course, this one here is narrower. And in fact, this is going to have a cutoff frequency much higher than this one here. And really, there is no way around this, unfortunately. If you have a tricky way to do that other than this, please write me in the comments. I would appreciate it. Okay, ladies and gentlemen, so this is really wraps up the now there should be one part that I'm going to do, which where we take the M by N weights, windowing weights, which is like this, in this case, a Taylor, and then basically weight these with that and try to get the side lobe to be lower than this, like I did in the previous parts, like we did for the single one. As you can see, this was a single one in here that I showed you where we did the reduction for the where the side lobes were reduced by using windowing technique on the slot displacement. But this is really much more complicated, and it's going to take me time because obviously in that case, you can't really duplicate all of them at once. You still need to create 8 unique ones, and then the displacement in here. You can see the displacement in here, of course, it's what I'm talking about is this one here. You can see the displacement in here is uniformly distributed, okay? Where that's what I'm talking about. Where the other one in here, let's see. Okay, where you see this one in here, look at the displacement. It tapers off to the ends. The end ones is where you get the lowest, the closest to the center line, where the middle ones, you can see here, these ones starts out large distances and they decay according to the window taper, okay? These are the coefficients. And of course, the coefficients are generated these from the MATLAB, and they're right here. You can see them right here. So you can see we started out in the middle, it's 2.5 millimeter all the way to the end side, which is roughly 0.94 millimeter. Okay. Now, this is easily done for a single waveguide. However, for an array, an aperture like this, it's a little bit more complicated. So, okay, gentlemen, ladies, this is it. I would appreciate, now again, like I said, if you have any comments, please go ahead and reach out to me via email. Also, you could call me at this number. I operate out of Jordan, Jerash, Jordan. My rate is very reasonable for consulting. I work remotely with the clients all over, except countries where I'm limited by the trade agreements that I can't deal with. Other than that, you can always reach out to me, and the first few hours, like I said, are free consultation. Until the next time, I thank you very much. Please visit my channel and sign up for the channel and share it if you like. I would appreciate that. Okay, ladies and gentlemen, thank you very much and have a great day, night, whatever time it is where you are. Thank you very much. Cheers.